Welcome to the unit on pre-engineered manufactured buildings, also commonly referred to as PEMB. On this first slide, if you were to first glance at it, you might not realize that all these buildings have something in common. That common factor is that they are all pre-engineered metal buildings. What makes them apart from each other is how they are finished out. A lot of times when we think of pre-engineered metal buildings, we think about your storage buildings like the one on the top right, Dollar General, O'Reilly's, but PEMB buildings can take on any look. As you can see from the list on this slide, there are many, many uses for pre-engineered metal buildings. So what makes a PEMB different than a regular building? In a regular steel building, the engineers begin with the architect's drawings and develop from there. With a PEMB, the engineering calculations are already done. You just select the appropriate materials for the situation. Other difference is with a regular steel building, the steel components are typically larger and of a heavier grade. With a PEMB, they are smaller with lighter steel components, therefore easier to put together on the job site and to handle with fewer people. Another difference is on a regular building, there is definitely more cutting, fitting, and welding to be done on the job site. With a PEMB, the components are pre-sized, prefabricated, and numbered, similar to putting together Legos. So it makes construction go a lot faster, a lot easier, and with less cost. Another difference is in regular construction, there's more equipment involved on the job site, tools and more expertise to erect, therefore taking longer to construct. The PEMB is like a kit and can save a lot of construction time, which in the long run saves money. Pricing wise, regular construction can run from $16 to $22 a square foot, and a PEMB typically runs about $16 to $18 a square foot. Again, a lot of it is going to depend on where you're located and the materials that are accessible and the location of the site. So we need to learn how a pre-engineered metal building is put together. One of the pieces that's involved is called the eave strut. The eave strut is a structural piece spanning columns at the edge of the roof. If we look on this picture on the right, if you look to the front edge of the building up on top of the beam, you'll see a shape that's similar to the shape in this drawing, and that is the eave strut. It is usually on the low side of the slope on a building like the one that's in the picture. The next part of the building is called a purlin. This is a horizontal beam along the length of the roof resting on a main rafter. If you look in this picture, you see the triangular shape, that is the beams. In the walls, we kind of have the same situation. We have columns, and then on the outside of those, we have the girts to help it to resist the wind load. Also, we use the girts to help frame openings for doors and windows. At the very bottom, where the metal panel attaches to the concrete slab, we have a base angle. And you can see that it attaches up behind the metal building panel and comes down below the concrete slab, and it has what we call a drip edge on it. That way, if water does get up in there, it can run back out and drip out. This is a way to keep water out of the building. The next part are the roof and sheeting panels. Again, this is where you can get the distinct look for your building. If you look at all three of these examples, they're all extremely different. They also come in many, many colors. They can be very simplistic, they can be vertical, they can be horizontal, they can be materials that look different than what they actually are. So there are lots and lots of choices. Here's an example of a roof and a wall sheeting panel. Again, they come in various widths. The one on the left is a 3-foot wide piece of sheeting. The one on the right is also a 3-foot piece of sheeting, but you can see they have a different pattern to them. Again, that can affect the look of it. A lot of times that is directed by the supplier, how they manufacture their products. Here is an example of some that are 16 and 12 inches wide. You notice that they each have like a little lip on them, and that is so that they can overlap each other to try to keep water out. That's very, very important, so they kind of lock into each other. The main part of a pre-engineered building is going to be the columns and the beams. Don't forget that columns are vertical, beams are horizontal. We call this a rigid frame system. Basically, the beams and the columns are tied together to form a rigid frame. The purlins that you can see in this that are kind of running towards us on the roof, and then there should also be wall girts whenever they get to that point. So what kind of loads do we have on buildings? Again, we're not getting into the engineering aspects, but it's still very good for you to understand that there are two different kinds of loads. There are live loads and there are dead loads. Dead loads are the intrinsic weight of a structure, excluding the weight of the people or goods. So when we look in the code book, for each type of building, it's going to give us some dead load requirements that we have to meet. For instance, a warehouse building will have a different dead load than an educational building, because potentially you could have a lot of weight with things being stored in a warehouse type facility. Your live load is going to be things that we really can't control, like snow collecting on the roof, furniture that changes. And you can see in the example below some examples of that. So here is a wall section or a rigid frame section. This should help you understand how it goes together. And again, they're all, depending on who manufactures it, they're all a little bit different. When I worked on O'Reilly's, we worked with like 3 different PEMB suppliers, depending on where we were at and who O'Reilly wanted to use at the time. And each building was built a little bit differently, even though we ended up with the same square footage of buildings, exterior walls, roofs. The way that it went together was different. You are expected to know this section. You should know what the roof sheeting is. You should know what the purlin is. You should know what the eave strut is. Gutter and downspout typically come with a PEMB. Here is the girt in the wall, there in the middle. Then you have the wall sheeting on the outside, and you have the base angle. Notice that in the concrete there's an anchor bolt sticking up, and it is coming through the base plate of the column. Typically, when we do a pre-engineered metal building, we have an anchor bolt plan. The anchor bolt, as you can see, goes down into the concrete, so it's placed when the concrete is poured. It's kind of an L or a J shape. That way it cannot pull out of the concrete. They leave it sticking up however far the drawings suggest, and then they come in and they set the column with its base plate, and then they tighten it down with the bolt. So the diameter of those anchor bolts, the length that sticks out above the column base, and how far it goes down into the concrete are all designed by an engineer, not the metal building people. The metal building people supply the building and they do the engineering for the building part, but the structural engineer actually has to design the concrete, the anchor bolts. We typically do an anchor bolt plan. What an anchor bolt plan is a symbolic representation of layout of anchor bolts in the building's foundation floor system. It is a plan view drawing. Always remember, anytime we have a plan view drawing, we're going to have 2 things. We're going to have a grid system, and we are going to have a north arrow. So now we are basically starting a list of things that we need to do when we do structural drawings. 1, we need to understand that columns are vertical and beams are horizontal. When we get ready to draw a plan view, we always typically need a grid with our plan, and since it's a plan view, we need a north arrow. The rigid frame again consists of the columns, which are attached to the anchor bolts, and then the beams attached to the columns. So the location of the anchor bolts is critical. If the metal building people say that the anchor bolts need to be spaced this distance for the plate of the column, we need to make sure that we have the anchor bolts in that location, because once they're poured into the concrete, they're really hard to change out because there's a lot of things you have to do to make that structural again. So it's very important to check and double check your anchor bolt locations. Here's an example of an anchor bolt plan. This is out of your book, and as I mentioned, this textbook is not the best book. So for this, it does have some general information on it. One thing you will notice is that we have some overall dimensions of the slab. That is very, very important. Then we have center marks dimensioned where the center of those anchor bolts are located. Again, those dimensions are very, very important to be on there. The other things that are important to be on there is how far those bolts are off of the edge of the slabs and how far apart they space off the center line. We would identify the edge of the concrete slab so that they know what we're looking at. So to draw an anchor bolt plan, the first thing we need to do is lay out the external dimensions, length and width of the concrete floor and plan. Typically on our plans, we try to put north to the top. Most of the projects we're going to be doing in here, we will just put our north arrow going to the top unless I direct you differently or you get a drawing that directs you differently. Then we're going to go in and we're going to lay out the center line grids. We need those in place first and make sure they are placed properly to be able to do this. Now we're going to do these drawings for the metal building in AutoCAD. So once we get our grids laid out the way we want them, we are going to lock them because the last thing we want to do is accidentally move one of those. Once you get the grid laid out, you need to put the dimensions on there. I typically always do that before I move on because if those are wrong, it's going to affect everything I do down the road. Again, when we go through this, we're going to do it step by step, so I will help you with that. Then we need to add notes and a section view of the foundation flooring system to show the vertical placement of the anchor bolts. Again, like in that section we saw previously, that is very important. This drawing here is an example of the anchor bolt. Then it has an enlarged section of cutting through where one of the column placements are located. And then to the right, it has a blow up of the area where the column sits. And then it has some foundation notes. These are all critical things that need to be on the drawing. Now, I will say the drawing on the far right in the bottom corner does not match the rest of the drawings. Again, this book is not very good. There are some typical notes that are on the detail itself. One, it says the column is to be recessed 6.5 inches below the finished floor. Then it also says the column by ABC, meaning that is by the PEMB people and not the contractor. 1/2 inch expansion joint, we'll talk about that here in a minute. A 6x6 10-10 welded wire mesh. A vapor barrier. And then it has some rebar in it. That's what the 12-6 each way represents. So let's talk about the parts and pieces here and how this gets done. Typically what they do is they're going to come in and they're going to dig out where the footings and foundation need to go. In this particular case, we don't really have a foundation. We have slab on grade, and then we have footings or the bearing locations at each of the column locations. So that's what we're seeing in that section where you see 6 foot square. That means under that column, there is a 6 foot square of concrete that is 1 foot 4 inches deep. So they come in and they dig out where these need to be, and then they compact the soil underneath it, and typically there is some gravel put under there, but again, this detail does not show that, and then that is compacted. They put their formwork in that forms the 6x6 by 1 foot 4 dimensions. Then they add the rebar in. The rebar is basically a metal rod, and it can vary in size. If you see a number 6 rod, that means it is 6/8, which actually equals 3/4 of an inch. If it says number 5, then the diameter of that reinforcement is 5/8, and it's running in both directions. So if you could look in on this and see it very clearly, you will see that there should be bars running towards us, and those are represented where they're cut as a circle. And then right above that, you're going to see the dash line that's representing the rebar that's running the other direction. Then you see where the column is coming out of the concrete are the two anchor bolts. Again, these are designed by the structural engineer, not by the metal building people. So the structural engineer designs the footing, determines how big it needs to be, and in this case, this one is square. They're not always square. And then he tells them what rebar needs to go in there, how far off the bottom of the footing that rebar needs to be, and how it's to be tied together, if it's to be tied together, and then where to place the anchor bolts and how far up the ends of the anchor bolt should stick out of the concrete and how far it should go down when it makes its turn. And then the spacing of those anchor bolts comes from the PEMB supplier. So they have the footings, and if you went and looked at the job site, you would see a 6x6 concrete footing, and you would see two anchor bolts sticking out of it. Once they do that, they come in and they make another form there where the column is to go, and in this case it's 2 foot square, and they'll make a form there that leaves a 2 foot square area centered on the column. And then they will come in and they will pour the floor slab. If you look at this floor slab, you see that we have an expansion joint. That will be right up against the form that they've put in to keep the concrete out from around the column. Then they will come in and you see another dash line that kind of curves up from the expansion joint and is over into the concrete slab. That is called welded wire mesh. In this particular case, it is a 6x6 10-10 welded wire mesh. So the wires make 6x6 squares, and the 10-10 is the thickness of the wire that is used. They use little stirrups to keep this up off of the bottom of where they're going to pour the slab, to where it's usually typically somewhat centered in there, but again, the engineer designs that. And then they come in and they pour the floor. You'll notice out to the edge of the footing, it angles back up, because at the edge of the footing, we have 8 inches of concrete, and it angles up and it goes to 4 inches of concrete. This is called a thickened slab. We do that to give it a little bit more structural integrity at that point where it's connected, because concrete can be not very strong in tension, where it's very strong in compression. We're going to do a detail that's similar to this, so we'll talk about that a little bit more when we get to it, but that's kind of what you're seeing here. The other thing you'll notice on this sheet are some general foundation notes. On the details themselves are what we would call specific notes or keynotes. Then we have general notes. The first one says concrete shall be 3,000 psi in 28 days. When they pour concrete, it really has no strength. If you see them pour it, it's like a mushy, watery type material, and they put it into the forms, and then it has to sit there until it hardens. At 7 days, they will test it for a certain PSI. At 14 days, they will test it for a certain PSI. And then at 21 days, they will test it for a certain PSI. And then when they test it on 28 days, it should have reached the 3,000 PSI strength. And when they pour this concrete, they'll pour some little additional cylinders. And with those cylinders, then at 7 days, they can take a machine that can test the strength and put force onto that piece of concrete in that they've saved, and it will tell them what it takes to make that fail. So at 28 days, it needs to be at 3,000 psi. Another thing that's on there, it gives the information about the vapor barrier. If we look back up at the detail, we actually have a vapor barrier in between the slab and the grade. Concrete is a porous material, so it will soak up the water. So we want to make sure we have it. The next thing it says is all reinforcement bars shall be grade 60. As with most types of steel and metals, there are different grades. So that particular grade is meeting the requirement that the structural engineer would like. Need to verify anchor bolt size and locations with building manufacturer's drawings prior to concrete placement. So as an architect, I get the information, and as a structural engineer, we get the information from the building manufacturer. Sometimes changes get made, and so once we get those drawings back during the shop drawing process, again, we want to check to make sure our drawings match their drawings. And then the contractor, before he ever puts them in place, he should verify again with the building manufacturer to make sure that they are in the correct location and the correct size. This says the anchor bolts shall have a 3-inch projection and extend to the lower 1/3 of the footing depth. So again, I had said that they will leave a portion of the anchor bolt sticking up out of the concrete, and that tells us they need to stick up 3 inches. That gives them enough room to put the base plate and put the bolts on the anchor bolts once they're in place. If the footing is 1 foot 4 inches deep, that is 16 inches, and it says the lower third, so that would be a little over 5 inches. So that where the anchor bolt makes an L shape or a J shape, it needs to be within the bottom, basically 5 inches of that footing. Then it says anchor bolt strength shall be A36 grade. Again, this goes into the strength of the materials that they're using for these anchor bolts. That's all we're going to cover today on the PEMB. We are going to go from here, and we're going to go ahead and draw the anchor bolt plan. And then on the next class, we will continue with the PowerPoint and continue to complete our PEMB drawings. If you have any questions, be sure to let me know. The next part of the video, we will go through step by step on how to do the anchor bolt plan.